Hello everybody. Let's do another problem. We're actually going to revisit lowest common ancestor of a binary search tree. The last solution that I had actually didn't treat this like a binary search tree. It treated it like a regular binary tree. So we visited every node. We didn't take advantage of the fact that all nodes on the left side are smaller than all nodes on the right side. So let's reread this problem. Given a binary search tree, find the lowest common ancestor LCA node of two given nodes in the BST. According to the definition of LCA on Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in T that has both P and Q as descendants. So let's think about what that means to have P and Q as descendants. Let's bring up a little notepad here. Now, if you're looking at a tree and you have any node here, what does it mean to have P and Q as descendants? Well, if you're at the root node, let's say this is the root, P and Q are for sure some descendant in here, right? And in this problem, I believe they guarantee that P and Q are descendants, right? So P is not Q, P and Q would exist in BST, that is a given. Now, given P and Q are descendants, do we know if it's on the right side or the left side, right? So everything on the left side is smaller. Everything on the right side of this node is larger. So at any node, let's use their example. Let's use 6 here. Let's take example 2. There's a 2 here, an 8, 0, 4, 3, 5, 7, 9. Okay, so if P is 2, let me just restart this. If P is 2 and Q is 8, right? If you're given the node 6, you already know that the 2 is on the left side. Now, you don't know where it is on the left side yet if you're just given the node 6, but you know that if it does exist, it's on the left side, right? So, here's the 2 here, right? You know that 2 is on the left side of 6, right? But even if you didn't know, even if this was an invisible tree to you, right? This is just an invisible tree. You know that it's going to be on the left side. And if this was also a tree where you didn't know the values, you know that 8 is somewhere here, right? Here's 8, here's 2. Now, if this is the first time you encountered this, you know that the 2 is on the left side, you know that the 8's on the right side, then this is actually the lowest common ancestor already. You've already found it. Now, let's think through it. Let's say there's a 6 here, right? And immediately there's a 2. And let's say there's a lower thing. So let's say there's a 7 here. And to the right of that 7, there's an 8. You may think that the 7 is lower. But once we go down to the 7 level, 7's no longer an ancestor, right? The 2 is not down here. So this here isn't valid, right? The 2 is not down here. So if you're at any node, the first node that you have, if you see that on the left and on the right, the P and the Q's are somewhere below this, you know that this is the lowest common ancestor, right? As long as it's one side or the other. So let's think about it. Let's iterate through every case where the P and the Q's could be, right? So let's think through, given a node, there's some subtree here and some subtree here, right? So the P and the Q could both be in the left subtree, right? If the P and the Q are both in the left subtree, then maybe the LCA is somewhere over here, right? You don't know yet until you look, right? Now, what if it's on the other side? What if it's on the right subtree? Well, if it's on the right subtree, it's a similar problem. You don't know where the LCA is, but it's probably somewhere here, right? It's somewhere down here. So the LCA is on the right side, on node.right, and on this side, the LCA is somewhere node.left, right? So what other case could there be? Well, there's another case where, given your position, the P or the Q are both on opposite ends. If they're on opposite ends, then you know that this is the LCA, right? Also, what if the P and the Q, let's say there's only one, that's the P right there. Well, right, and if the Q is not in here, right, if there's no Q in here, well then actually this is the Q, right? If this is the Q and you have this position, this is still the LCA, okay? And then it's the same if the P was here, this is the Q, this is the LCA, right? So if you're writing a function that takes a node, there's only these cases, 1, 2, 3, 4, 5, that you want to look through, right? So what's case 1? Case 1 is that both P and Q are smaller than the current node, right? So let's look at case 1. So case 1 is P is smaller than the node's dot value, right? And Q is smaller than the node dot value. And in that case, we know that this node is not the lowest common ancestor. That is somewhere down here. So in that case, we could just return the recursion. So we recur of, node.left, right? They're both smaller, so we return node.left. Now what's case 2? I'm just going to color these yellow so you can see it. So what's case 2? Case 2 is that the P and the Q are over here, and that means the LCA is somewhere in this subtree. It is not this node. It cannot be this node, right? Because this node only has a left child and a right child, and only one of its children contain P, right? Only one of its children can contain Q. So if P is larger than node.value and Q is larger than node.value, then we want to return the recursive function like this, right? Node.right. Now, what about these cases? In case 3, then the P is somewhere and the Q is somewhere, right? But what's actually interesting is this is the else case. The else case is all 3 of these combined, right? So in the else case, P or Q is split left or right, and then P or Q is singly in left, or P or Q is singly in right. Well, in that case, what is LCA? LCA is just a current node, right? So LCA is just, let's just return this node, is this node right here. And that insight is from the fact that this is a binary search tree. In a binary search tree, you actually know which direction you want to go, right? Based on the cases that you're looking for. So let's code this up and let's just take a quick look, right? So you have a go function. I'm going to call this a go function. I'm gonna make this a pass for now, and you're gonna first pass in the root, right? Maybe we can just return whatever's coming out of here, which means that this has to return a tree node. This would be a type, right? And then this has to take a tree node, and that's what root is, right? Root is a tree node, and go returns a tree node. So it's just those two cases. It's case one is P and Q are both in left. Is case two, P and Q are both in right. And in that case, we have to continue on because this node is not it. And then in case three, really otherwise, this node is the LCA, right? And this is from 3, 4, and 5, case 3, 4, and 5, where the LCA means that P and Q are on opposite ends, or that P or Q is on one end, and you know the current node is P or Q. So let's just look at these cases. So it's actually P.val. So if P.val is smaller than node.val, and Q.val is smaller than node.val, then we just want to return the recursive function. Actually, this should not be root because it won't always be root. It's going to be node. It's just going to start as root in the first time, right? And we're also, this also helps a lot because based on the problem, we know that P and Q both exist. So we don't have to check for, you know, edge cases. So if this is that, we do this. Otherwise, P.val is larger and Q.val is larger. Then we return going right. Otherwise, and this is the else case, then we actually just return the node because this node will be the answer, right? And you would think we'd have to write all these if statements, like if P or Q is split between left or right, and then also if P or Q is singly existing in left or right, or if P or Q, you know, we split these into two ones, singly existing in right, so singly existing in left or singly existing in right. Then we return node, but we don't have to actually. So this is just the else case. We return node because if these two conditions aren't true, if we're not continuing to traverse, then it means that we've already found at least one of these, and that this root node or this node is the one that we're looking for. So it's just an interesting use of the BST, that BST property. It should reduce our runtime significantly. And there we go. We beat 96% of users. And this, you know, I thought the solution before was acceptable. But now that I think about it, you really need to at least try to exploit the fact that you're in a BST. Even if you don't end up doing it, you have to at least acknowledge that it's in the problem. Whereas before, completely ignored it. All right. Thanks a lot.